So, continue with the last lecture which we are discussing on lateral load on piles. We are going to talk in the last lecture we have talked about introduction, then conventional method of analysis, elastic method using Winkler approach, and now we are going to apply whatever we have discussed in elastic method using Winkler approach. If you recall, in that method we have defined a coefficient called coefficient of modulus of subgrade reaction eta h, and that eta h is for the sand, while for clay there is no variation in modulus of subgrade reaction from which it is assumed, and we will be doing using those we will find the solution for piles in cohesionless soils as well as for clay. Then we will also discuss design procedure and finally one numerical example. Here is the solution for piles in cohesionless soils. So, what you could see, a typical pile length Ls and stiffness EI is shown in this figure. So, this is your pile. In this pile Ls is the length from pile head to tip, EI is the flexural rigidity, and Qg and Mg are nothing but Qg is the lateral load while Mg is the moment acting on the piles. Naturally, you know the value of Qg, you know the value of Mg, you know the value of length of the pile and the flexural rigidity. Now, when this pile is subjected to the moment as well as the lateral load, our objective is that the pile will get deflect as shown in the figure A, and the deflection will vary along the pile length. Naturally, the deflection will be 0 if I consider particularly end bearing pile at the pile tip, while maximum expected is at the pile head, because you are applying the load at the pile head itself. So, this kind of variation is expected, but how this deflection will vary with the depth, that is our basic problem today. And once you know the variation of this deflection with the depth, then rest of the things can be find out. For example, if you want to find the shear, then it will be dy by dx. What is d here? One need to understand x is along the pile length, while y is along, normally x is this direction and this is z, but here you need to understand that what we have considered, x is along the depth while y is in the horizontal direction. So, the y will be representing the deflection direction, that is yx. Yx means this deflection is a function of x, the depth, and the shear, that is the slope, s is slope which is dy by dx, and once slope is known, then you can find the moment which is ei di square by dx square, and then shear force, and then finally soil reaction. So, what you have here in this case, that the soil modulus variation for the, because we are discussing for cohesionless soils where it is assumed that kx equal to eta h into x, where kx is nothing but this can be treated like a. So, once you know the deflection, then you can find the rest of. Now, here because we are assuming that the solution for cohesionless soils, that is for the sandy soil, and for the sandy soil this kind of variation, that is the variation with the x along the depth of this modulus of subgrade reaction can be eta h into x. That means when this will be the linear variation. So, as we already discussed, the variation of the modulus of subgrade reaction is linear, where eta h is nothing but the value at the end, and it will be 0 at the top. So, this has been already discussed in the last lecture. So, what you have, the figure A shows the curve yx curve of the pile. Once this is known, then we can do rest of the things can be found easily as we discussed. Now, the issue is this one, that how to find the deflection y with respect to x, that is the basic problem. So, relative stiffness factor in this case is defined by L alpha by lambda, where L alpha is nothing but characteristic length and lambda is a positive integer. So, L alpha is infinite length of piles, and that is we have discussed, that is that length after which there is no change in the deflection due to pile length for a given load. So, that things we have discussed, that even if you are increasing the length after that, but there will be deflection will remain constant. So, L alpha divided by some positive factor, that is relative stiffness factor T, and T is not dimensionless, rather T will have the unit of length. Okay. So, now what happens, this deflection y which is along the depth will be a function of many factors. first thing is x, where you want to find x is a variable. So, as the x change, naturally the deflection will be different. Then it also depends on relative stiffness factor T and Ls. What is Ls? Ls is shown in this figure, is total length of the pile from pile head to tip. K, we already talk about K, that is the modulus of subgradation. EI is flexural rigidity of the pile, and naturally it will depends also on the load which you are applying from the top, QZ and MG. So, this is depending 1, 2, 3, 4, 5, 6, 7 parameters. If deflections are small and if an elastic behavior is assumed, the principle of superposition may be applied. If Ya represents the deflection caused by the lateral load QZ and Yb is the corresponding deflection which is caused by Mg, then total deflection is given by Ya plus Yb, and in this case we can separate out the deflection due to the QZ and deflection due to the Mg. So, Ya by QZ can be represented by function of x t ls k e I, that means QZ and Mg are taken separate, and this is, so 4a and 4b are representing this. You could see now that on both 4a and 4b right hand sides are like you have the functions of same parameters, but different functions, one is f a and one other is f b, but the functions parameters used for those functions are same for both cases to find the deflection. What is Ya? Ya is the deflection due to the lateral load, while Yb is due to moment, and total deflection is y equal to Ya plus Yb. But one need to understand that this is can be done when you consider the principle of superposition is valid, that means for the elastic behavior, and we are considering here elastic behavior of the soil, we are not considering the nonlinearity of the soil here. So, this theory is applicable when we say the elastic behavior of the soil is considered. Continue with this. So, now equations 4 can be written in dimensionless form, and for this dimensionless form what you need to understand that you have in both equation 4a and 4b you have 6, 5 is coming here and one is QZ and Mg. In both the cases you have total 6 parameters, and but all the 6 parameters are consist of only 2 things, one is length or another is force. For example, x, t, ls, ei, anything can be represented by force unit or length unit. So, as a result you can have out of 4 independent dimensionless form. So, it is shown here for case A, you can be represented deflection can be normalized with respect to Ya into Ei divided by QZ t cube. So, all these will be dimensionless. Here T is a parameter which is relative stiffness factor, it is then x by t, ls by t, kt4 or Ei. So, you could observe that in all the 4 terms T is coming in picture, the same thing is for case B. So, now let us say what is these different parameters here, x by t is dimensionless and that is represented by capital Z, that is called depth coefficient. Then ls by t is the maximum value of Z, which is Z max and maximum depth coefficient. The next kt4 or Ei is soil modulus function which is represented by phi Z. Then Ya Ei by QZ t cube is Ay which is deflection coefficient for case A, and Yb Ei Mgt square equal to By which is deflection coefficient for case B. So, naturally when you are using QZ then it will be QZ t cube, when you are using Mg then it will be Mgt square. So, that is there because it is ultimately need to be dimensionless. So, this is how we have defined these parameters, and after that we go continue with this. Now, what happens once we represented in this form, the total deflection at any depth x is sum of Ya plus Yb. What is Ya? Ya is due to the QZ and Yb is due to Mg. So, you have Ya can be represented Ay QZ t cube or Ei plus By Mgt square Ei. Now, if you know the value of Ay and By and rest of the parameter here in this equation 7a is known to you, then you can find the value of deflection at any depth x, at desired depth x. Naturally, the parameter Ay and By will be also varying with the depth, they are not going to be constant because rest of the things QG t cube Ei and Mgt square Ei they are constant with the depth. So, only variables in this equation 7a with x is Ay and By. Same thing is for the next equation 7b which is written for the slope, where As and Bs are function of x, and third equation 7c is for moment, Am and Bm is also function of x, and then shear force 7d, Av and Bv is the function of x, and then finally for soil reaction Ap and Bp are function of x. Now, if these coefficient A and B with their subscript, if it is known with their variation with x or z is known to you, then naturally you can get from these equations whatever you want you require, let us say for your deflection, slope or moment or shear and soil reaction. So, let us work on this, that how we can get the value of these coefficients and this. So, what is done from the theory of beam on elastic foundation, the equation of deflected beam can be written as, so soil reaction is simply EI d4 y dx4, right. So, equation 8a is basically equilibrium equation, where you have on right hand side soil reaction, and while on this left hand side you have the deflections and then slope, and then you have derivative of this multiplied by EI. However, the value of P is given by minus ky. So, P equal to minus ky, and if I put this value of P, so this is equation 8b, and if I put this value of P equal to minus ky in the next this equation which is in equation 8a, then you can get here. Why the negative sign is used? Negative sign is simply showing that soil reaction will be in the acting in the opposite direction your deflection, because the soil reaction will try to oppose the deflection. If deflection is downward, soil reaction will be upward, if it is so like this. So, this is the case here. So, that is why this negative sign P equal to minus ky is used, and when we put this value of P in equation 8a, you end up here in this equation d4y dx4 plus, and then this can be, and for case A and case B it can be separated in equation 9a and 9b. Okay. So, that simply with the subscript. Now, the issue is how to solve these equations. So, before we solve these equations 9a and 9b, using this dimensionless form which we have shown here in equation 7a, and these parameters in equation 5 and shown in 5a 5b, we convert equation 9a and 9b into dimensionless form. Simply what you need to do, put the value of ya in terms of ay, and then use phi z also. So, here phi z is, you need to understand phi z is nothing but kt4 or ei. So, basically this kt4 or ei will go here. So, here you need to understand because basically what you have x is t dimensionless parameter, you have x over t is z. So, x over t is z. So, I can show how it is coming, x over t is z. So, what you can have x equal to t z. So, dx will be equal to t into dz. So, this manipulation is done in this equation to get equation 10a and 10b. So, using this you get these equations both 10a and 10b. So, once this, the difference between 9a and 9b and these 10a and 10b is simply that they are represented in dimensionless form. Now, this equation have converted in terms of z and this. Now, we solve this equation and this solution will provide the value of ay and by. So, what is done here for this solution for the case A. So, this is what you have, this is okay, this is written again 10a and 10b is here. So, dimensional form. So, this is the same equation 10a and 10b, and for a solution of equation 10a and 10b it is necessary to specify phi z and to define the value of t. So, for sands k equal to eta h into x. So, this is the case here, and other soils where soil modulus may be varying. So, what is done here, phi z, which is phi z is what we call here, phi z is shown here, that is soil modulus function, and this soil modulus function in this case this is dimensionless, this is equal to z, where z is also dimensionless. We need to understand z is not length, rather z is but x by t. So, both are dimensionless on the left hand side as well as. So, that means the what is the soil modulus function phi z will be proportional to x, because t is constant. So, if it is equal to z, that means as the z varies phi z will vary, or we can say in this way that phi z is simply proportional to z, and so that is basically proportional to with the depth, and naturally it will be varying with the depth. So, with this 11a, if I put the value phi z and z in this equation, then I get kt for ei, and that is nh x t for ei and x by t, and after this manipulation you got t equal to ei eta h over 1 or 5. Now, equation number 12 is very important, and in this equation what you get, you find the value of relative stiffness factor T for cohesionless soils, and this is important for all the further calculation. But one thing I will like to point out here, that T is simple, it looks a very simple equation, but it have very important practical meaning. EI is nothing but the flexural rigidity of the pile. So, your EI carries the E, which is Young's modulus of the pile, and I will depends on the diameter of the pile. So, EI will carry both material and geometrical property of the pile, number 1. Second thing, eta h will carry your soil property. So, in this parameter T, you will have the geometry of the pile, you have the material property of the pile as well as soil property, all are represented, and as the value of EI increases, T will increase, or eta h decreases, T will decrease. So, it is a relative stiffness between pile and soil, and this factor will govern everything in this analysis or design. So, Reach and Matlock in 1956 used the finite difference method for equating the coefficient A and B for finding the deflection y and slope s, moment m, shear v and soil reaction p, coefficient qg and mg. So, what is done here? So, naturally as we discuss that, first of all the rest of the things we are going to discuss is based on finite difference method. So, Reach and Matlock using the finite difference method, they try to calculate the value coefficient A and B, and these coefficients are for deflection, slope, moment and shear force, and these coefficients are found separately for soil reaction coefficient for Qg and Mg. So, they have that has been found separately for Qg and Mg. Piles with Z max less than 2, the pile behave as a ridge pile, and Ay and By linearly decrease with the depth. So, this is like in the figure. Let us first let us see that some figures. Okay. In the figures, actually they have shown some figures, and in the figures when you could see for Z max 2, there is no change, that means the deflection decreases as this value of Z increases. So, that behavior of the pile is linear. For Z max greater than 5, Ay and By are more or less same, and thus pile length beyond Z max is not effective, and this Z alpha is 5 times of T. So, that means it can be concluded that for this length of the pile, when you are this length or Z max 5 up to Z, if Z is greater Z max is greater than 5, then pile can be called as cylinder pile. Pile may be treated as a cylinder, piles, and we need to make sure before we apply the Reach and Matlock approach that the value of Z max is greater than or equal to 5. But normally in practice you will get that this Z max is more than 5. So, that will not be a problem, but if your Z max is less than 5, then the approach which we are discussing should not be applied. So, these are the two tables which has been proposed by Reach and Matlock and these researchers. So, let me put it like this, Reach and Matlock. So, what we are going to is discussing is basically Reach and Matlock approach. So, the first table gives the coefficient A for long pile. Long pile means basically for both the cases, long pile means Z max is greater than 5. So, that, and that is why in this case if you see in both the tables, the value of these coefficients are given up to Z equal to 5, because after that it is assumed that there is no change in the values of these coefficients. So, what you have here, the first table that gives the value of A, Ay, As, Am, Av, Ap. The same thing is for coefficient B. What is observe? You observe for the long piles, the value of Ay you could see is continuously decreasing, and then it becomes negative. As have some variation, Am also is the 0 at the top, and then it start increasing. For AV also it is maximum here and then decreasing, and AP have also variation, and AP does not like initially it negative values, it goes negative and then it becomes positive. Similar kind of variation is there, but if I check the variation, there is a between AM and BM there is a difference. AM is increasing with the depth, while BM is decreasing with the depth. So, that need to be understood, and that may have its effect on this. And one more important point before I go ahead, I will like to see that these tables are derived for the case when your pile head is free, totally free, it is free for deflection as well as rotation. So, this is assuming pile head is not restrained. So, this is I can put with these tables before you use pile head is free. So, both the tables can be applied when pile head is free. However, when you apply some restraint on the pile head, for example, you say that there should not be no rotation, no slope will be there. So, those conditions can be derived easily, and we are working on that. So, these tables are the coefficients are for pile head is free. Now, when we consider a case when the pile head is restrained against rotation, that means basically your slope will be 0. So, you treat like this one. Let us say I consider a case where I apply a lateral load only on the pile, no moment is acting, okay. Then in that case I need to use table 1 only, right. But suppose you, and this table 1A is the table A, this table first table is for the case when your pile head is free. But if I keep my pile head restrained against the rotation, then what will happen when I apply some lateral load, it will be subjected to some moment when you restrain against slope like then some moment will be generated. And for to use this solution, I need to find the equivalent moment even if you are applying the lateral load. So, what is in this case? The slope, assuming slope S equal to 0, where S not equal to SA plus SB given by this relation, and then what you have here that mg if in this equation I put this one, and solving this equation mg by qgt is nothing but as and bs where at z equal to 0, and from these tables I put the value of as and bs for z equal to 0. So, for z equal to 0 you have this minus 1.623, and for bs you have 1.750. So, as a result finally you end up here the value is minus 0.93. So, what ultimately you end up, that value of mg equal to minus 0.93 qgt. So, you can understand like this, that a pile which is restrained against rotation at pile head can be treated as, and so it is let us say problem given is this one, you have a pile which is subjected to lateral load only, no moment, no external moment is acting on the pile head, only lateral load is acting, but pile head is fixed, pile head is fixed against rotation. This is same equivalent to another pile whose pile head is free, that means pile head may be subjected to rotation, and in addition to lateral load a moment mg is also considered. So, this mg will take care of your the condition which you are applying, that slope should be 0 here, because once you, in addition to qg you consider this value of mg, this will make effectively the rotation at the pile head equal to 0. In that case we can use the same table, both table 1 and table 2, even for the condition when the pile head is restrained against rotation. But in this case even the pile is subjected to lateral load qg only, but we need to require to use both the tables. So, this is the equivalent moment generated. So, you can say what is mg, mg I can write equivalent moment due to restraint of pile head, due to restraining of pile head, and this restraint is against rotation. So, continue with this. solution of for piles in cohesionless soils. For once you have done this one, then what we have for deflection, now you have y a plus y b, a y q z t q plus, and we have substituted the value of b y where m g we put equal to from this equation, m g is minus 0.93 q z t. So, ultimately you end up here a y minus 0.93 b y, which where c y, where c y is nothing but a y minus 0.93 b y. So, this was the case when you are applying say what is called the complete fixity for the pile head. But if your fixity is partial, then in that case you can have, instead of c y can be represented a y minus lambda 3 0.93 lambda b y, where lambda is 0 for free head, lambda is 1 for fixed head, and lambda is 0.5 for 50% restant. So, the equation 16d can be applied for all the cases, whether your pile head is free or fixed or what that. So, if it is free, then lambda should be considered 0, there will be no effect of moment, and when lambda is completely fixed, then lambda is 1, and if lambda could be, so lambda values of lambda in this is basically lambda will be between 0 to 1. So, it is that it, and both values are included. So, the value of lambda will vary between 0 to 1. With a similar approach, you can find the moment also, where Cm is Am minus 0.93 Bm, and m can be calculated from this relation as 17C, and then same for the soil reaction also, ACP AP minus. So, this way this completes for solution for piles in cohesionless soils, and then we will discuss in the next lecture for the solution for piles in cohesive soils and design procedures, as well as one numerical examples. So, I stop for today's lecture here, and thank you very much for your kind attention. Thanks.